Well, I think we can start. Welcome back, everyone. We're finishing off week 9 so far, and that means we're going into our second exam just next week. I don't have too much for announcements other than we're on example 2 in section 5.2. I posted this software here for an application problem that we're going to do at the very end. We've wrote pseudocode before. We'll do it again. We're going to prove the pseudocode actually executes as intended by using mathematical induction. But just proving it is not good enough. I think we actually have to run the code. And so that's why this is here. Not something you have to download. It's not something I'm going to require you do in homework problems. Think of that link there as more just a classroom demonstration on seeing if our pseudocode even runs and does as intended after we prove it should by mathematical induction. So that's what's going on with that brand new link. I should have posted that the prior class. Sorry about that. And then the other bigger announcement, of course, is that exam 2 is going to be on next Monday. Apologies to all the students I said Tuesday. For some reason, I just can't get it straight which classes start on Monday, which ones start on Tuesday this semester. And it's already past midterm. That's kind of embarrassing, but here we are. We'll still get through it. Our content is going to be on the propositional logic, sections 3.2, 3.3. And both of these documents here are a very accurate representation of all the questions that could be asked. Things to watch out for in these sections are, you'll also be looking into determining when you have a tautology, determining when things are logically equivalent. And so there's lots going on there with just truth tables itself. And again, looking through these problems here is going to give you a good representation of what those could look like. These sections here, we're dealing with quantifiers and then nested quantifiers, but nothing too different than what we did in class, what we did in the homework problems. I'm not going to ask too many tricky interpretations going from English into the quantifiers, because those are pretty difficult problems. You need extra time to really consider them. And 4.3, finally, this one is kind of like a big application, really, to everything we did in chapter 3. I'm only going to ask one proof, since asking a bunch of proofs just doesn't seem nice on a real timed exam. And just by way of hint on the proof I'm thinking of writing, I'm probably going to go for the proof by contrapositive method, because it really does a lot. It forces us to look into logical equivalences, forces us to think about the implication, and show how to prove an implication by forming the contrapositive. So that's going to be probably the question that you can expect as a proof. Same as the kind of problems we did in the lecture notes, as well as the solutions here, stuff about numbers being odd or even after you multiply them and so on. But the contrapositive method was the one I'm going to go for on that one. And that's kind of my big rundown on the announcement so far. We talked about the formula sheet last time. This is a good one to have ready to go in front of you when you're studying, but don't bring it to the exam. It's going to be on the last page. I have the solutions to these on the Moodle website. Just scroll up to the relevant sections. And on Friday, I'm going to begin working on these. That's probably going to be the first thing I do on Friday. So I should hopefully have solutions posted sometime in the afternoon. Well, any questions at all, folks, about either one of those announcements or otherwise? Okay. All the question I have is, any questions that folks have about the exam 2 material content itself? Any review problems you'd want to take a look into? Maybe even older homework questions, things like that? Okay. Well, with what we're going to get going today, we're going back to section 5.2. And also keep in mind before we jump back into there, if over the course of, say, Friday through Monday, you're studying on exam 2, if any question comes up at any point, don't hesitate to email, reach out somehow, some way. I'll be happy to engage with you and work on that problem, even if you're emailing on the weekend. These weeks, when we go from a week into an exam week, I'm pretty busy too, so I'm probably going to be at my computer checking my emails quite a bit. But let's take a look at what we left off on in section 5.2. It's a rough problem to jump into. Let's break this down on what we did slowly, starting right about here. We're proving something by the technique of mathematical induction. And the idea here, let's grab this just for easy reference. If I can figure out how, there we go. The idea with mathematical induction is need to start a sentence when I'm ready. Hang on one moment. The idea with mathematical induction is we first prove a base case. We call either P of 0 if it starts at 0. We prove P at 1 because the relevant statement was about integers starting at 1 and going larger. So that's the base case. We have to show P of 0 or P of 1, some starting integer. The predicate function that we define is actually true. After we verify the base case, the major step next is the so-called inductive case. In the inductive case, what we're trying to prove is an honest implication that if we assume the predicate function at n-1 is true, then we can use that assumption to derive that the predicate function at n itself is true. In this way, we generate a long list of implications that sweep out through all of the integers whatsoever and really verify the claim that for all n and z greater than or equal to 1, P of n holds. And in our problem, this is P of n. That the summation equation of the squared integers from 1 to n could be re-expressed in this way. A degree 3 polynomial function divided by 6. Kind of weird in a way. But this is the structure of what we're trying to prove on in this kind of problem. The statement here, in the base case, let me not scroll too far, we had to show P of 1 is true. We started at 1 because that's where the integers start for this claim right here. So if we show P of 1 is true, what we do is we just set n equals to 1. Then we work on both sides of the equation. We have to wonder if n is 1, what would happen to the left-hand side? On the left-hand side, we computed and got this out. And notice the change. It's a summation from I equals 1 to n. Now it's a summation as I goes from 1 to 1. So all we do is just plug in 1, square it, and get 1 as an output. That verifies that the left-hand side is 1. So now we need to see that the right-hand side is also 1. So we just grabbed it, computed it out by setting n equals 1 right here. And that gave us the 1 we're expecting. That did it. That's the base case. P at 1 has been verified. Any questions, folks, about that step there? Okay. Well, on the next case, it's kind of like a proof by cases, but not exactly. It's as if we're thinking in case 1, we do one check on the predicate function. But then it's not exactly proof by cases because in the inductive case, we're showing that the predicate function holds for all other integers n by verifying this implication here. And you know, one thing I should have said when I wrote this proof out, looks like that was an oversight, was I should have specified the next integer. We started at n equals 1. Down below here, let me see if I can kind of sneak my way in. For the inductive case, we should say next, let n be greater than or equal to 1. Not a serious omission I would complain about in the homework, but it helps with clarity because if you state that right there, back up here, that's essentially what we're doing. For a generic value, n greater than or equal to 1, we plug in something. Oh, and let me make a change here. That should be greater than or equal to 2. I got mixed up because if we start at 1, we go 1 higher. In the generic form that they put out, they start at 0, and then they go 1 higher right here. But if you start at P at 1, then over here, you would say n greater than or equal to 2. So all the next integers right after. So that's something that does deserve some clarity. This is the way the author stated induction, yet it looks like a lot of problems I have actually start at 1. That's kind of a strange disconnect. So next at n equals 2, the idea with the inductive case is if we're going to prove this implication, we just start by assuming that is true right away. Pn-1 is a statement, it evaluates to true. So we went up here, re-changed the summation because we're talking about n-1 now. And here's how it reconvened. Summation as I goes from 1 to n-1. This n turns into n-1. N plus 1 turns into just n. And 2n plus 1, carefully checked, became 2n minus 1 when we plug in n minus 1 and do some algebra. So we assumed that is the truth about this formula, that some integer greater than or equal to 2, maybe 2 itself, maybe 5, who knows, we are assuming it holds as true directly. And our goal after that is we need to arrive at the conclusion P of n itself is true somehow, doing a bunch of algebra, some logic, some cleverness. Arriving at Pn is true means we're trying to get to exactly that formula right there. So that's how the inductive case starts. Assume the truth of this formula. That's the predicate function at n minus 1. We're assuming it's true. Next, well, how do we prove Pn is true? It's kind of like how we proved P of 0 is true, actually, or P at 1, rather. We start with the formula itself. So that's where we started. Right here. We began the summation, and our goal is to get to the right-hand side by doing a lot of algebra. But this is the second time we've seen this trick. If you're proving something with a summation by induction, oftentimes what you do is you take the full summation from 1 to n, partition it into a summation to n minus 1, and then just add the next term. The next term is n squared because if we take the index I, when it goes to n, we throw it inside I squared, it outputs n squared as its final term. And the only reason we want to do that, and this is the second time we've used this strategy, is because now we have a tremendous substitution. Through the green color coding, this is our assumption that we made in the inductive case. So we can now just throw in that whole formula right exactly there. This is where we admitted we didn't have enough time to finish the problem. Sorry about breaking the problem across a couple days. From where we are right now at this stage, our goal is to do enough algebra, as much as it takes, to arrive exactly right here. In fact, let's take a screenshot with this. This is where we're trying to end up. So let's put it down below and use that as a guide as we do some algebra. Any questions at the moment, right here and now, in this stage of the proof, folks? Okay, let's move forward. I think probably the only thing that we can do if you see something like this is force the second term to be a fraction, add the fractions together. So this would then turn into, let's also distribute n inside. We may have to expand that entire numerator. So we'll get n squared minus n times 2n minus 1 over 6 plus 6n squared over 6. Now we have common denominators, so we'll add across the numerators. But just so we're not writing down a bunch of fractions, let me also expand this right here and then go plus the 6n squared. So expansion of this will give us 2n cubed. And then here to here is minus n squared. Distributing the negative n will get us minus 2n squared. And then finally, plus n. So that's our entire numerator, all divided by 6. And hey, at least we got one part, right? We've got the 6 down. If we can get all the rest, we're home free on this. So next step, let's just combine our like terms. That'd be the natural thing to do at this stage. So 2n cubed, can't do much with that, but we also have negative 3n squared. Hang on, let me try again. We have negative 3n squared plus 6n squared, so positive 3n squared altogether, plus n, all of which is divided by 6. Now we can get the n now because n factors out of our numerator, so we're getting even closer. N times 2n squared plus 3n plus 1, all divided by 6. So next part's done. And you know what, for the last part, we kind of know what we want, right? This is almost cheating in a way. I'm going to go n, look down below, n plus 1, 2n plus 1. That might not be right, so let's double check here if it really expands in the way we expect. We definitely get the 2n squared that we're expecting. We definitely get the positive 1 if we were to FOIL this. Here to here is 2n, and hang on, let me try again. Here to here is 1n. I forgot how to FOIL for a moment there. And here to here is 3n, which does hit that term. So it tells us we really got it. The assumption that the prior case, Pn minus 1, giving this formula actually holds, allowed us to take the summation of I squared, use the truth of that prior case actually holding as a formula, and generate the formula as holding true in the case Pn as well. That means we're done. We have proven the following. This shows the assumption of Pn minus 1 being true implies the next statement, Pn, must be true as well. Briefly, we just say Pn minus 1 implies Pn. And so the proof is complete. Deserves an exclamation mark because all of these are kind of weird, really. I think personally, proof by induction itself is a pretty weird technique. It really takes some time to really internalize what is going on when we do all these kinds of statements. What is the goal? So anything you can do to kind of step back from this, maybe for the person who likes to read analytical information, this is your version of stepping back. If you're the kind of person that likes arrow diagrams, this might be your version of stepping back from the problem. Let's pause right here. I think this is an easier one to analyze. In the proof that we just did, we showed P1 is true. We verified it directly. And then in the proof that we did next was showing this is true. We verified this directly. Once that's been verified directly, we can use the proof of P1 in this silly diagram. The proof machine is really this part right here, showing the implication holds. So P1 is true, and we just proved this holds for n greater than or equal to 2. Then we can just plug in, hang on here. Yeah, n bigger or equal to 2 will give us the P1. I had to double check the indexing here. Because this is true for all n greater than or equal to 2, we plug in the P1 statement into this implication, and it directly verifies P2 is true. But then you can plug the P2 statement back into the implication, which we showed holds for all n bigger or equal to 2. There's really a for all there. Then it verifies P3 is true, and then repeat forever, because we're talking about all integers. And it's in that way that we verified this statement right here. So it's hard to really see it sometimes when all the details are here as just like a cloud of work. So anything you can do to put in a nice break, just saying the base case, that's your reminder that you're showing P of 0 is true. Just simply saying the inductive case is the reminder that you're showing the implication Pn minus 1 implies Pn is true. And once it held for 1, it now holds for all n whatsoever greater than or equal to 1. So weird idea in mathematics, but it's really powerful. It gives us a clever way to prove a lot of different statements. We'll take on 2 more proofs, kind of like this one. Not all summations, because that would get too boring, seeing that technique over and over again. And then we'll do the application problem of writing down a function in pseudocode, verifying it does its intended with induction, and then actually executing it and looking at it from the second point of view. But before doing all that, let's practice a little bit more on induction with this expression right here. So next statement says, prove the following statement. For all integers n greater than or equal to 1, 5 to the power of n reduced by 1 is divisible by 4. Kind of a weird statement. I don't know if I believed it the moment I wrote it down on paper, but if we can convince ourselves through a proof, then, well, that's highly convincing. I would believe it then on if I was confident in every step of that proof. Really, the harder thing about induction is not necessarily verifying a base case, verifying an induction case. Another big challenge on induction is determining what you're even proving. What is the predicate function, Pn, that we're working with in the first place? So let's do exactly that. Let's take this whole statement and rewrite it as a predicate function based on n. A predicate function is only going to output either the Boolean true or false, but that true or false is based off a statement we put here, which would just be informed by that pi power n minus 1 is divisible by 4. So we have a predicate statement down. This is something that happens for z greater than or equal to 1. So we'll use that domain there and say we want to prove that for all n in z greater than or equal to 1, P of n holds. This is always kind of weird to write. You could say P of n is true, but if you leave it really terse like this, not saying much, what we're communicating is for every integer n, P of n is a true statement. That P of n holds, in other words. So this is what we're proving altogether, and we'll give a proof by induction. Any questions so far, folks, before we launch into this one? Okay, it's not a statement about summations or anything like that, so we get to use a different idea. But really, this one's going to be pretty similar to dealing with odd integers or even integers, that kind of statements there. First thing we want to show is the base case. Let's say what we mean by that. We must show P at 0 is true. So that means, hang on, let me back up. Should be P at 0, right? We're starting at 1. So let's say 1 right here, just to be specific. So let's show P at 1 holds. I think this highlighting might help me with that weird starting position on induction. To show P at 1 is true, we come over here and just input a 1. We have that. Let me put in a sentence here. Then, so we're not just starting with a sentence fragment, 5n minus 1 becomes equal to 5 to the power of 1 minus 1, which is 5 minus 1, which is 4. And yeah, 4 is divisible by 4. We were just lucky in that in the base case, it's a pretty simple statement, right? We just plug in a number and get a result. 4 is divisible by 4.
So sorry if I missed this, but with proof by induction, do you always need to have a base case that shows that P of n is true with the n being the first value in our range?
Yeah, absolutely. So in proof by induction, we always have to start right here. Whatever the value is up here, the minimal value, that's our base case. And so yes, we must always show base case must hold for our first step. Other questions about that so far? Okay, and good news is we're done, right? P of 1 was just a statement 5 power 1 minus 1, which returns 4, is divisible by 4. So we can say immediately, this shows P of 1 is true. And I'm really glad that you mentioned that about the base case, because sometimes you can have kind of a misadventure in mathematical deduction where if you skipped the base case, but you were still able to prove Pn minus 1 implies Pn, this can be done with statements that are actually patently false. So I could put down a false statement down here for which the inductive statement could come out as true, but the base case is false, meaning the whole statement itself is a false statement. There's counterexamples right at the base case, for example. So there's a lot of really wacky looking proofs where you can make some statements that look incredibly false. Someone claims they proved it as true by induction, but the flaw in the proof was they never showed the base case. That's why everything looks broken mathematically. But let's go now to that harder case, the inductive case. So we're separating out our proof basically in chunks or paragraphs. We're done with the very first phase. And in the next section, the inductive case, We also use another proof writing technique where we say what we want just to kind of direct our mind on what we should do next. If you always say to yourself in the inductive case, we must show Pn minus 1 implies Pn. And again, it gives your mind kind of a structure of saying, what should the next steps be? Maybe the next step should be to say what n is in the first place, right? We started at 1, then we must show the implication down here for some n bigger than or equal to 2, one integer higher. We leave that integer arbitrary. We can't pick one. So we're just going to say n is greater than or equal to 2, show that this holds. Because we're proving an implication in the inductive case, the very first step now is assume Pn minus 1 holds or is true, however you like to phrase it. And then instead of a colon, let's just say here, this means if we're talking about Pn minus 1, we go up here and just adjust the index n to an n minus 1. So this would mean back up here, 5 to the power n minus 1 is divisible by 4. Now we're ready to really get started. The base case sometimes does require some creativity, but a lot of times it's just a really fast verification. Inductive case always goes like this, and then once we made the assumption Pn minus 1 is true, now we have some creativity that we have to use. But you know, like, this is a concept that's pretty close to what we were doing in section 4.2, 4.3, like we mentioned. If you say 5n minus 1 is divisible by 4, then here's your immediate consequence. Then there exists an integer k, so I'll say exists k in z, such that 5n minus 1, if you're divisible by 4, it also means it's a multiple of 4. So we can write in 4 times k. So this is the essence of divisibility by 4. If we said divisible by 91, we would just say 91 times k. But that's a huge statement we put down because, like in a lot of problems, we need to access the Pn statement to verify it's true by doing something algebraically. And until we put this on paper, there was no algebraic structure I could really work with, manipulate. But now we can. Let's adjust or work with that statement there with the goal of trying to get back up here. We want a conclusion 5n minus 1, not 5n minus 1 minus 1. 5 to the power of n reduced by 1 is divisible by 4, based on the assumption 5 to the power of n minus 1 reduced by 1 is also divisible by 4. Let's start by going like this. Next, I'm going to just grab this part so we can work with it in a little bit more of a cleaned out space. 5n minus 1 equals 4k implies another equation right away. Now we have to do something algebraically, but if you're paying attention to the Pn statement, it might inform you what you really should do next. Let's look at both of these boxes simultaneously. The major thing I want to get the proof to go through is 5 power of n right there. That's our goal, that's our hope, that's our big want. Now in the equation down below here, I need to do something legal algebraically to both sides of the equation to force that spot by the red dot to be exactly 5 power n. Anyone see what we must do?
Do you multiply by 5?
Good call, Corbin. That's the major idea on this one. So if we multiply by 5, we get up here. And if we can connect with a divisibility by 4 statement, get 4 times something in place of k, our work is done. But notice how crazy that is. That's the natural thing to do, but If you didn't think of it, we're just sort of stuck in the water on this one. Maybe there's another way to do it, but I think that the other ways might involve massive amounts of ingenuity. So we're ready to get going. Our goal now is to place some integer in this spot multiplied by 4. Let's even highlight the 4 there. We can get to that spot. The value that's in place of k in blue might be a lot more complicated, but if you can convince yourself it's an integer, we're home free. So let's take that step. Multiply this equation both sides by 5. Scroll a little bit more. We're running out of space pretty rapidly on this. This would then imply 5 to the power of n minus 5 equals 20k. And I think we need a screenshot. You always want to have your eyes up here. When you're in the inductive case, after you've assumed Pn minus 1 holds, keep your eyes on the prize right here. This is our major target we're trying to get to, divisible by 4. And look what we have so far. We have the 5n minus 5 power n. We don't have the minus 1, but if you're looking here, it informs you of the next step. Just add 4, and we'll get the minus 1 we're expecting. So last equation implies 5n minus 1, because I've added 4, is 20k plus 4. We've now matched up this segment of the predicate function. If we can get divisible by 4, our work is done. And recall, divisible by 4 means our right-hand side needs to involve 4 times some integer. We're basically there, right? Just factor out the 4. Let's write down one more implication. Last equation implies 5n minus 1 equals 4 factored out, leaving behind 5k plus 1. That is an integer for sure. If I had, say, 5k plus 1 divided by 3, we have a problem. That just depends on k, if it's an integer or not. If I had to take a square root, problem as well, because this being square rooted may or may not be an integer. But if it's an ordinary combination like this with multiplication, addition, subtractions of other integers, it's automatically an integer. Let's say here, 5k plus 1, maybe a comma helps, is an element of z. And so this finally implies 5n minus 1 is divisible by 4. Let's match up a little bit more highlighting here. Divisible by 4 specifically because it's 4 times some integer. That's what we were trying to show, that 5n minus 1 is divisible by 4. So our work is done. We assumed Pn minus 1 holds. Now our final statement here is that this implies Pn holds as well. You'd probably look up to see the Pn statement up here to really read that out, but we'll look down so we don't scroll as much. That means right at this stage, the proof is complete. Well, any last questions, folks, on getting to that last step? See if we can step back on this a little bit. Barely. So here's the original statement. Here's the quantified statement we're proving over here. And base case, again, is just verifying that this is really true at 1. The troubling case is usually the inductive case, working through proving this implication right here. Any questions at all, folks? Proving Pn minus 1 implies Pn. Okay, well, let's try out to one more. Then we'll give the application problem another try, or a try. So here's the last one. And it is another summation one, sorry about that. It seems like summation formulas are just very common when it comes to adduction. And, well, at least these are similar to the problems that you have on the homework assignment as well. So we want to prove another statement for all integers n greater than or equal to 1, that if you take 1 times 1 factorial, 2 times 2 factorial, and so on, all the way to n times n factorial, you get n plus 1 factorial minus 1. We haven't worked with a lot of factorials so far in this class, so just so that we're all on the same page, let's just write down some simple examples. If you say 3 factorial, all you mean is you're taking 3 times 2 times 1 for a 6. Likewise, if you say 4 factorial, you are doing 4 times 3 times 2 times 1 for a 24. The times 1 is curious because it does not affect the product, but it's a good idea to put it in because it reminds us that we can have a structure where a factorial is giving us that many terms. Except there's a breakdown somewhere down the line. 1 factorial is 1. It's just, well, 1 factor and nothing to multiply by itself. Here's where it gets weird. By convention, we've designated 0 factorial to be 1 as well, so that's pretty odd. Any questions about these statements so far, about the factorial function? Okay, well, so far as a function, n factorial is a function, well, how would you even designate that? N is the input to the function. So it's not like f of x, right? It's more like f of x going this way. That's how the factorial function is really designated. And usually if you are saying what the function f does, you do something like this, f maps x to y. So if we're trying to do the same thing, say domain and range of the factorial function, we would just say exclamation mark maps from integer z greater than or equal to 0 to integer z greater than or equal to 0 as well. That's not exactly the range, that's a codomain, but that's what the factorial function is doing, taking an integer, outputting out another integer. Weird notation though, right, when you really think about it. And next thing we can say, just for a little bit more practice with factorial, is if you write out generically n factorial, what you mean is n times n minus 1 times n minus 2, and we use this little trick here because we don't know how large n is as an integer to say and so on. Finally, 3 times 2 times 1, with the understanding that if n was maybe a 2, it would really start here, the 2 times 1. So that's the n factorial function. But one thing to think about whenever you write down a factorial function is that you can associate chunks of it. If you associate this part, where n is just left over, the part in purple is n minus 1 factorial itself, because it starts at n minus 1, multiplies all the integers dropping by 1 until we get to 1. That means you can take an n factorial and re-express it in any which way that might be convenient. Say, for example, you could write that it's n times n minus 1 factorial using the idea above. And actually, that is convenient to us. We're going to have a reason to do something like that. So that's my 2 4-minute crash course on factorials. Any questions about them so far? Okay, I almost want to delete this because that's probably going to cause some questions, but let's let those questions happen. They're good questions. Designating a function mapping can be confusing when the way you specify the function itself is non-standard, like the factorial function. So now we're ready to take on this claim. It's a summation formula, so to even get started on this, it might be a good idea to say the statement is P of n as a predicate function will be a summation as I goes from 1 to n, starting at 1, because this formula is indexed at integers starting at 1 as well. And what's the format? We go I times I factorial. That's actually kind of hard to look at. So I is the index at what we're summing on. We're also going to do a factorial, much like the 1 factorial, 2 times 2 factorial. So we get this whole structure. When n is 3, say, 3 goes in here, and you get 3 factorial. And that's the third term of the sum. So we want to prove that this summation now, expressed more compactly, becomes n plus 1 factorial minus one. Actually, this is not quite the right format, but we'll discuss on how we get to n plus one factorial once we get to that step. So this is the claim. We want to show it holds for all n and z. So let's just say here to guide our thoughts, we're proving that for all n in z greater than or equal to 1, we usually go with a colon. Let's do that again. Pn holds as a true formula. So we're ready to get started. We'll give a proof by induction. Any questions about the formula or otherwise before we get going on this one? Okay, as we discussed earlier, very first thing we have to show is this formula is grounded in something. We might be able to prove the implication that Pn minus 1 implies Pn, but it does us no good unless it's grounded in some foundation. We'll start by saying let n equal 1. Maybe let's start by organizing. Let's start by saying what we're doing. This is the base case. And now we can say let n equal 1. We will show P of 1 holds or is true. Okay, starting at 1 only because of here. Also, it's where the summation starts. So now let's say at n equals 1, we first focus on the left-hand side. Let's just see what this turns out as. We'll get summation I goes from 1 to 1, I times I factorial, just a one-term sum, and we'll get 1 times 1 factorial. But 1 factorial is 1, like we discussed up here. So this is just a 1 times 1 altogether. We output a 1. At the next step, we're looking into the right-hand side of the equation. If we don't get 1, something's gone massively astray. Maybe we made a small mistake. Maybe it's possible I typed up the problem and just made a weird typo. Maybe it was supposed to be a minus when it was written in as plus. Something's gone terribly wrong. But let's check. At n equals 1, n plus 1 factorial minus 1 becomes 2 factorial minus 1. 2 factorial is just 2. So this becomes 2 minus 1 equals 1. And now we have shown this holds. We have equality in the middle. So we'll say this shows P of 1 is true as required. It's not required to say it as required, but it's just kind of a way to end your statement here to say we are totally done with the base case. That's all we need to show. Now onto the inductive case. It's a summation formula, so we're going to use that same exact summation trick to make the inductive case work. But you know, it always looks a little bit different every time you change the statement here. And this one does look different as we go to run through those steps. So here's the big step. The inductive case. So let's say first, where we start, we'll begin by saying, let n be bigger than or equal to 2. So one integer higher. We specifically say that because we don't need to treat the n equals 1 case any longer. It's true. It's all about what happens on the next cases. So we let n be greater than or equal to 2, and we must show Pn minus 1, so one integer backwards, implies Pn. So back up here, that would be the original formula that we're trying to verify. So next thing we do is we assume the truth of Pn minus 1. Let's just directly say that. Assume that Pn minus 1 is true, so that we get this whole formula right here. Not exactly though, right? When we say Pn minus 1 is true, keep in mind the formula itself is indexed by n. So we're doing an adjustment here and an adjustment here as well. So we'll have summation I goes from 1 to n minus 1. Same structure, I times I factorial equals, now over here, it's n minus 1 plus 1, so just n, factorial minus 1. Okay, already that's a pretty big step, right? It's organized by writing down this stuff each and every time. If over the course of doing all the inductive proofs on the homework, studying them for again on exam 3, if you always wrote out these steps, it becomes like a methodical process that you do each and every time. It will remind you that you go back up here, re-index to n minus 1, and now you have something strong to work with. That's a big assumption that the formula works at n minus 1 here. Then our goal is to show Pn is true. Because we have limited space, we're going to drop it down here. But if you were doing this as, say, like a homework problem, I think the thought is you'd just be looking at the top of the page often to double check how close you're getting to this statement right here. Oh, let's not do that. There we go. Just to guide our thoughts, we'll say here, we next prove Pn is true. We prove the truth of Pn just like we did in the base case. The only difference is we don't know what n is, but we still start on the left-hand side this time. We're going to do a bunch of algebra until we get to the right-hand side. Much like what we did over here, we started on the left-hand side, cranked it out, and this is the difference. We are also able to put something in on the right-hand side as well. We can't do that any longer, but at least we have a direction. Start right here by the red dot. We have summation as I goes from 1 to n of I times I factorial. And standard trick with summation statements in induction are, if we assume this is true, all we need to do in the next step is partition the sum. We'll add up 1 to n minus 1, giving us this, and then add the final term. So this turns into I equals 1 to n minus 1 summation I factorial plus, because we only summed up to n minus 1, we come up here at m, input it into the expression below, and that's our final term, n times n factorial. Okay, so next thing we can do is make the gigantic substitution. Here, through our big assumption, we have a formula for this thing in the bracket. That summation turns into n factorial minus 1. So there's the big substitution there. And over here on the right, we have plus n times n factorial. And so far, we haven't matched it up with that too well, except we do have a minus 1. So I guess that counts, right? We're now trying to get an n plus 1 factorial out of this. So at this stage, well, we can try something. Yeah, question first?
No, I just decided.
Awesome. For me, actually, it's kind of foggy at this point. I wouldn't know for sure what to do, except we could factor, right? We could rearrange these terms, put them together, and factor n factorial out. But here's another idea. We haven't done this a lot, but sometimes when you're looking at your goal, do something to the goal itself. N plus 1 factorial is equal to n times, let me try again. Forgot how to do a factorial. N plus 1 factorial is n plus 1 times n minus 1 times n minus 2, and so on, till we get to 3 times 2 times 1. So if we can get something like this going on, there's a not factorization, but a partition and all these multiplications, all these factors, we would see that n+1 and factorial is just a different way to write n+1 factorial itself. Again, that's connecting up with these thoughts we were writing up here. So this is another weird technique where we're looking at what the goal is, seeing how we might get there so we can be informed on what algebra to actually do up here. So next step, let's bring the factorials together. N factorial plus n factorial minus 1. Let's factor out that factorial. I want to factor it to the right and leave behind then n+1 n factorial minus 1. So we get the n here when n factorial is factored out. The +1 comes from here with factorial factored out. But n+1 times n factorial, it's not always easy to see, but that's n+1 factorial. The guide is down below here on how we get there. This is nothing but n+1 as a factorial function minus 1. That hits our target finally. But again, notice how we got there. We looked at what n+1 factorial is. It can be rewritten this way, which meant the moment we got to this statement here, we can connect it and just say, altogether, that's n+1 factorial. Coming back here. That's a lot of arrows. I think that's even confusing me. But any questions at the moment, folks? With getting to that last statement here, n+1 factorial minus 1. Okay, well, it's definitely a cause for celebration because what did we just show? We showed that the assumption that Pn minus 1 is true will also imply Pn is true. Our work is done. We just need to wrap it up. Lots of ways to end the proof. You could say, this demonstrates what we required. The proof is over. Or you could say, if you'd like, we have shown Pn minus 1 implies Pn holds. And so the proof is complete. Then standard way to end the proof is to include some special symbol. You don't have to do that. But on this page, it's not a bad idea. My symbol for ending a proof right here is just a way to say everything below is just scratch, but let's put a border down just for extra emphasis. I do want to leave the scratch behind this time because it really conveyed one big, well, really huge step going from here to here. And my view is not always easy to see. But that's how we did it. We reverse engineered how it should form. And then we made the connection right here in line. Well, that's all the mathematical induction proofs I had. Next problem we'll go into is the application problem. But any questions or comments at the moment, folks? Okay. Well, because I felt like we might have extra time today, here's the problem that I was thinking about for an application to all of this. It's a home-brewed problem, so it's something we're going to just write in right here at the end of the notes. And let's say for the application, write out pseudocode that implements the factorial function. Because we've been talking about factorial, this seems like a good natural next problem. Let's add a little bit more, namely, just to be specific on what we're doing. We're trying to implement n factorial. Now let's say even more. Give a recursive definition in the pseudocode. Can never seem to spell that right. So let's give this a try. What we're writing out this time is a function, so it's a little bit different when we were trying to give pseudocode for something that was doubly quantified. So lots of different structures for writing out a function. Usually the way I write it out, because I use R quite a bit, is I go by naming the function first. Let's call this fact, short for factorial. I'll save us a little bit of writing. Then I'll say factorial is going to get the function structure. And I need just one argument, one input. You'll take an integer n. So this is how I'd probably write it out. Depending on the coding you've done, you might say function first and then specify factorial next. But because it's pseudocode, the understanding is you just turn it around to however you need to in the system you're using. Now we'll put in a curly brace to say this whole block is for defining the factorial function. And with the recursive definition, we can start with an if-else structure. Let's say if n, this is the n that's going to be passed to the function. So when we go to actually use it, we'll say factorial, parenthesis, give a value of n. But when it comes to factorial functions, you want to say what happens right at 0. That's like the very first value. So if we check it, and it is in fact a 0 that was passed to the function, we'll return to the definition of the function itself, the output to the function, 1. And this is because 0 factorial is 1. So that's the idea of that return. Then what we do next is, well, we have to give a definition for the factorial function for all other integers n. For example, we know that n factorial is n times n minus 1, n minus 2, 3 times 2 times 1. So we need to incorporate this idea. And here's how it goes. So let's say else. This is if the user, when using this function, gave not a 0, but maybe a 1, maybe a 5, maybe 1,000. We'll say else, return. Well, what should we return? Let's say someone gave us n. We'll have to take n times. Well, recall, that's just n minus 1 factorial, right? So right over here, let's call the function we're defining at the same exact time. Return n times the factorial function at n minus 1. That's wild, right? Because what I've done, and this really looks badly circular, but somehow it's not, this is weird. I have referred to the function within the definition of the function. It's not circular. This is just what we mean by recursive. We have a recursive definition. And when you look at n factorial, it's really the same thing in spirit. You calculate it by taking n times n minus 1 factorial. Well, that's just essentially what we're doing right exactly here. So let's end this right here. And that's our function. So we wrote out the pseudocode that implements it. Now, next thing we need to do is imagine it's a much more complicated problem that you're solving, something that is high stakes. Maybe you work in government, maybe it's a corporate field, and you have a really convoluted process that you're implementing, maybe across databases. You have to prove to yourself somehow what you're about to do really works as intended. So that's what we want to do next.
I have a question.
Yeah, go ahead.
So if your base case is when n equals 0, would your answer not be 1 over the intended answer? Because you would add 1 twice.
Let me see. So in class, what she was saying is we'd be multiplying by 1. So it wouldn't quite matter as a 1 there.
Oh, yeah.
Gotcha. And you know what we could do next? This is the part where I was mentioning, grab your favorite way to compute. Maybe it's C, C++, Python. I'm going to use R through the IDE RStudio. And let's actually run this. Let's implement this and see if it actually is giving us a factorial. So I think that's a great way to kind of do these kind of problems. If it's just pseudocode, it looks kind of like this stuff. It's hard to make any meaning out of it unless you're examining every little part highly, highly carefully. But let's see if we implemented it right by attempting to run it. So let me go to this environment. This is a program called R. R is a weird name for a, but it's based off something called SPSS, which is a corporate product for statistics. So people decided they didn't want to pay any money for it, and they open sourced it, called it R instead of S. It's based on C, ordinary C, and Fortran. Kind of a weird lineage on it. It's not the most efficient system out there, but it gets the job done. So the way we would implement this is go fact for factorial. Left arrow is just a way to say store into the factorial thing, a function. N is going to be the argument. We'll say if, and 0, return 1. So that's us defining the factorial function. And this is the really, really weird spot. Else, return, n times the factorial function itself just defined at n minus 1. Running this gave us a function. And now below in the console, we can test it out. Factorial 0 had better give us a 1, right? We're good on that. How about factorial 3? That's 3 times 2 times 1. Yeah, we better get a 6 out. Looks like we're on the right track, right? We could go factorial, how about 4? That's 6 times, excuse me, that's going to be 4 times that 6, the prior answer. It's the right thing, 24. So it looks as though it's right. This is going to do the job for us. But remember kind of the context here. This problem is not so much about the factorial function. It's more about if you had something really, really complicated going on, you would write out the pseudocode, you would implement it, you would test it out. But this is not a perfect test, right? I can't demonstrate it's going to work at every potential value. We might think it might. It looks pretty plausible already. But if this was a really complicated problem that you're solving, this is just not sufficient. A few outputs. We want to prove that this is going to give us for every integer n the right output, the output to an honest factorial function. So just knowing it works on a few test values still isn't sufficient, depending on how high stakes this is, of course. Not super high stakes for a factorial function, but imagine a context where things really are pretty big deal if it goes wrong. We'll say next, prove the pseudocode does in fact implement the factorial function. We're going to prove this with mathematical induction. So that's our connection to this, calling it an application. Any questions so far, folks, before we give it a try? Okay. Well, first, we really want to be careful with what we're proving in the first place, right? Let's say it this way. In any proof by induction, we started with a predicate function indexed on n. So Pn this time is going to be the statement that's either true or false. Fact, referring to the factorial function up here, returns n factorial. So that's the statement that we want to connect to what we did up here in the pseudocode. But what we're actually proving is that for all n in z greater than or equal to 0 this time, so this is a pattern break, factorial starts at 0, so we're going to start our statement here at 0 as well. For all n in z greater than or equal to 0, p of n is a true statement. So we'll just say tersely p of n. Our proof will be by mathematical induction. Which means, just like before, we have to start with the base case, then we'll go through the inductive case. But the proof goes a little bit differently this time. Everything that we're trying to prove here this time is based off this structure. So that's where we have to pay really close attention. How did we define things? How does the code actually execute in the very first place? So that's what we're doing majorly in this kind of proof. But the rest of the details are exactly the same as what we've been doing all along on every step of the way on these nodes. We begin with the base case. But notice the indexing this time. We're starting at 0. Let n equal 0. We must show p of 0 is true. Well, how do we show p of 0 is true? We go down here and see exactly what happens. Let's make that happen right here. At n equals 0, and let's see, it's saying in fact is just kind of weird. Let me say this better. In the pseudocode, let's see what happens. We begin with the function. All it does is begin with a if then. But if we set n to 0, this is the block that's executed right away. In the pseudocode, if n identically 0, block is executed. That's because that's exactly what it does. If you pass it 0, then if we get the check as true for n equals 0 in the comparison, we return 1. The block is executed, and fact 0, now I'm talking about the factorial function, returns 1. That's exactly what it should do. We can say next, we were looking into the pseudocode. We saw what the factorial function returns, and it better return an n factorial in the case n is 0. So let's say next. 0 factorial itself equals 1, and that's what we had to check. Pseudocode returns 1. We know 0 factorial returns 1. So we really have n factorial here at the value of when n is 0. This shows P0 is true. So we know our pseudocode down below is actually anchored in something that if we run this, it's not going to run forever, because if we give it a 5, it will start decreasing the values here recursively until we get to 0 and it'll stop. So that's what happens in the base case. Now we have to do the difficult work of track through the inductive case. It's really not too bad. It's just we have to take interesting points of view, right? We have a predicate function. The predicate function is referring to pseudocode, so we have to think of the pseudocode as well. And the pseudocode is trying to implement the factorial function, 3 big functions altogether, if you're regarding the pseudocode as a function in its own right. So lots to track, and here's our next step. The inductive case. Remember, there's a really big purpose to all this. This was a complicated algorithm. Verifying just a few outputs is never good enough for us. If this was high stakes, your company or your governmental organization could be in terrible, terrible shape if something goes wrong with this code. So we're verifying not for few runs, for every possible integer n, this all does as intended. And we start by saying, well, where do we begin? N is now greater than or equal to 1. Next, we make an assumption. Well, let's say first, we must show Pn minus 1 implies Pn. We assume Pn minus 1 is true, so let's say that down below. Assume Pn minus 1 is true, so that what happens there? Well, you'd be plugging n minus 1 up here, factorial n minus 1 returns, or if you say equals here, that's fine as well, returns n minus 1 factorial. So what we just assumed in the inductive case is that that pseudocode works at some integer n, only requirement is that it's bigger than or equal to 1. So it in fact works at that 1 value. If the assumption that it works at the 1 value implies that it works at the next value, we have verified the pseudocode works as intended for all integers n all at once. So that's going to be our next steps on this. So this is a big assumption. Factorial n minus 1 returns n minus 1 factorial. Now consider Pn. So for considering Pn, let's track the execution of the function we defined, factorial n. So let's come down here, see what happens. First question is, does that block execute? I would see what would happen with this block here. It depends on n, so that's a tricky statement actually, right? But the one assumption we made on n, it's greater than 1. That means the if block does not execute. It only executes in one situation specifically. So we can say here, if n identically equal to 0 block, not executed, and we return from the else block. This is the only other thing that can be returned. We return from the else block n times factorial n minus 1. But we made a big assumption on factorial n minus 1. We said it returns n minus 1 factorial itself. And I'm going to have a slight abuse of notation here. Instead of saying what it returns, I'm essentially saying what it equals. So it's as if I'm placing an equality right here, just to not have as many words between essentially an equality. I'm going to write that this is going to be equal to n times factorial n minus 1. We assumed inductively in that hypothesis gives us n minus 1 factorial. But from our work of breaking up the factorials, n times n minus 1 factorial is itself n factorial. That's what it needed to do, return n factorial. So we can say here, as required. Because once again, once we got that n factorial, that was the goal up here. Factorial gets returned at the statement P of n. That means our work is done. We can just assert right here and now. This shows Pn minus 1. The truth of that statement directly implies through the implication Pn is true. And so the proof is complete. But even though the proof is complete, let's just say one more thing. Fact n, factorial function n, returns n factorial for all n in Z greater than or equal to 0. And again, it was a simpler kind of thing that we showed here. The pseudocode is not terribly involved, although it is kind of a mind loop because it's recursive at the same time. But imagine with any kind of application like this, you're doing something orders and orders of magnitude more complicated and higher stakes. That's the reason why you'd really want to carefully consider, does it really work? And the proof by induction is a natural way to show these kinds of things, especially in recursively defined functions like this. But any last questions at all, folks, before we call it a day? Okay, thanks for humoring me on this last problem right here. Even though we don't do a lot of pseudocode, mathematical induction feels like it's just not going to have a lot of value unless we actually implement something like this. But when we come back, next Monday, it's all gonna be about the exam. So just another reminder, if you all have any questions whatsoever, if you're studying, working on homework problems, don't hesitate to reach out. I'll be very happy to help. But have a great weekend, folks. Try not to work out too hard or work too hard, and I'll see you all on Monday.
Thank you.
Yep, take care.